Dear students, so today let us study about the topic coordination chemistry, that is the part 2. In the 5th semester, you have studied the basics of the coordination chemistry, that is the terms involved in coordination chemistry, then the nomenclature of coordination compounds, then you have studied isomerism, and then the Werner's theory of coordination compounds, effective atomic number, and also the calculation of EAN in various compounds. So today let us study the further aspects of this. That is, the various theories have been proposed from time to time regarding to explain the coordination compounds. Among that, the first theory was Werner's theory of coordination compounds. Second is the effective atomic number theory, that is the Sidgwick's theory. And today you are going to study about the valence bond theory. And further other theories are crystal field theory, ligand field theory, and molecular orbital theory. Among this, let us study the valence bond theory. So you know the syllabus of the 6th semester. In the 6th semester, so you have the valence bond theory as well as the crystal field theory. The other theories you are going to study in the higher standards. Coming to the valence bond theory. This theory was developed by Pauling, and it deals with electronic structures of the central metal ion in its ground state and a kind of bonding, and it also explains about the geometry and magnetic properties of the complexes. The main points of the valence bond theory are: the central metal ion makes available a number of empty s, p and d orbitals equal to its coordination number. These vacant orbitals hybridize to give an equal number of new orbitals of equivalent energy called hybridized orbitals. The third point, the hybridized orbitals orient in space to give definite geometry. The empty hybrid orbitals of the metal ion overlap with fully filled orbitals of ligand to form ligand-metal coordinate bond. The number of coordinate bonds in the complex is equal to the number of empty orbitals in the central metal ion. The d orbitals involved in the hybridization may be inner, that is n-1 d orbitals, or generally 3d orbitals, or the outer nd orbital, or the outer 4d orbital. The metal complexes where n-1 d orbital is involved is called inner orbital complex, or it is also called low spin complex. The metal complex where nd orbital is involved, that is 4d orbital is involved, is called outer orbital complex or high spin complex. The low spin complex is due to the pairing of the electron, the spin gets lowered, and in high spin complexes there is no pairing of electrons, hence the number of unpaired electrons becomes more, hence the word high spin complex. Now in all these coordination compounds, the coordination compounds have different hybridization based on the coordination number. If the coordination number is 2, then it is having sp hybridization where 4s and 4px orbitals involved in the hybridization, giving linear geometry with a bond angle 180 degree. The examples of such the geometry are the diamine argento 1 ion and the dicyano argentate 1 ion. Coming to the coordination number 3 complexes. These complexes are very rare and the hybridization in these complexes is sp2, where 4s, 4px and 4py are involved in the hybridization, giving trigonal planar geometry with a bond angle 120 degree. The example for this is triiodomercurate 2 ion. Coming to the coordination compounds with coordination number 4, they have either sp3 hybridization or dsp2 hybridization. In sp3 hybridization, 4s, 4px, 4py and 4pz orbitals are involved, giving tetrahedral geometry with a bond angle 109 degree 28 minutes. Example for such things are nickel tetracarbonyl and also the tetramine, the zinc 2 ion. Now, the complexes with dsp2 hybridization, where the 3d x square minus y square, 4s, 4px and 4py orbitals are involved in the hybridization, giving square planar geometry with a bond angle 90 degree. The example for this is the tetracyanonickelate 2, tetracyanocuprate 2 as well as tetracyanoplatinate 2 ions. Complexes with coordination number 5, they are very rare, and where here 3d z square, 4s, 4px, 4py, 4pz orbitals are involved in the hybridization, giving trigonal bipyramid geometry with a bond angle 120 degree and 90 degree. Example for this is the iron pentacarbonyl as well as the pentachlorocuprate 2. Now, coming to the coordination number 5, there is one more hybridization known as sp3 dehybridization. Here, the outer d orbital is involved. That is 4s, 4px, 4py, 4pz and 4d x square minus y square orbital is involved. In such cases, you have square pyramidal geometry with a bond angle 90 degree. Example for this is pentamine antimonate 3 ion and also you have pentacyanonickelate 2 ion. Now the complexes with coordination number 6 also have the inner orbital and outer orbital complexes. Here in case of inner orbital complex, 3d x square minus y square and 3d z square orbitals are involved, giving to the octahedral geometry with a bond angle 90 degree. And the example for such kind is the hexa aqua titanium 3 ion, hexamine cobalt 2 ion, hexacyanoferrate 2 ion. Now with outer orbital complexes, in this case 4d x square minus y square and 4d z square orbitals are used, and the example for such things is hexa aqua chromium 2 ion, hexafluoro cobalt 3 ion, hexamine zinc 2 ion are the examples. Now, the same what we have discussed so far about the valence bond theory. In this slide, the silent features of the valence bond theory are given. As I have said, the Linus Pauling in 1931 explained this valence bond theory. This bond theory satisfactorily explains the structure and magnetic properties of a large number of coordination compounds. The central metal atom or ion has the required number of vacant orbitals for accommodating the electrons donated by the ligands. The number of vacant orbitals is equal to the coordination number of the metal ion for a particular complex. In all these things, S, P, D and F vacant orbitals are involved. The silent features of valence bond theory, just in 4 points I have given. This vacant orbital goes hybridization to form the same number of hybrid orbitals. Each ligand has at least one orbital containing lone pairs of electrons. Vacant hybrid orbitals filled with ligand to form coordination bond. Coordinate bond is stronger if the overlapping between the orbitals is greater. Now, once if you know the valence bond theory, so we have to apply this valence bond theory to the various coordination compounds or the ions. Now, let us take the first example, that is the hexacyanoferrate 2 ion. Now, in this hexacyanoferrate 2 ion, the iron is the central metal ion with primary valency +2 and secondary valency 6. Secondary valency is nothing but it is the coordination number. Since 6 ligands are attached, hence the secondary valency is 6, and the primary valency. So the valency of iron we don't know, that's why we call it as X. Cyanide valency is -6. So -1, so 6 cyanide are there. So X minus 6 is equal to the total charge of the complex, that is -4. So that is X minus 6 is equal to -4. Therefore, X is equal to +2. This is how the primary valency of any complex compound or ion is calculated. The cyanide ligand is a strong field ligand. Therefore, what it does, it pairs the electrons. Now, let us take the atomic number of Fe is 26. Its electronic configuration is 3d6 4s2. Here Fe is in +2 state, hence the electronic configuration becomes 3d6. The ground state electronic configuration of Fe +2 is 3d6, which contains 4 unpaired electrons. When the strong ligand approaches nearer to the central metal ion, it gets excited so that unpaired electrons gets paired up. The excited electronic configuration of Fe2+ is shown here, where all the unpaired electrons gets paired up. There is no unpaired electrons, and we have 6 vacant orbitals which hybridize or which undergoes hybridization to form D2sp3 hybridized orbitals which orient in space to give octahedral geometry. The vacant orbitals of Fe2+ ion undergoes D2sp3 hybridization. Each cyanide ligand gives lone pairs of electrons to the central metal ion. There is no unpaired electrons in the complex. Hence, the hexacyanoferrate 2 ion is having octahedral geometry with a bond angle of 90 degrees. As there is no unpaired electrons, it is diamagnetic in nature. Since inner d orbitals are involved in hybridization, this complex is called inner orbital complex or low spin complex. So this is how you have to give the explanation. So whenever any complex ion is given, and explain the complex with the help of valence bond theory. So in your syllabus, they have given like this, the 6 different complex ions. Similar explanation can be given even to the VBT with reference to the hexacyanoferrate 3 ion. In this complex, Fe is the central metal ion with primary valency +3 and secondary valency 6. The cyanide ligand is a strong field ligand. Atomic number of Fe is 26. Its electronic configuration becomes 3d6 4s2. Here Fe is in +3 state, therefore its electronic configuration becomes 3d5, where all the 5 unpaired electrons are there in 3d. When the strong ligand approaches nearer to the central metal ion, it gets excited so that unpaired electrons get paired up, and excited electronic configuration of Fe+3 is shown here, which shows that it contains one unpaired electron. And as the vacant orbital of Fe3 plus ion undergoes D2sp3 hybridization, each cyanide ligand gives lone pairs of electrons to the central metal ion. There is one unpaired electron in the complex. Hence, ferricyanide ion is having octahedral geometry with a bond angle of 90 degrees. As there is one unpaired electron, it is paramagnetic in nature. Since inner d orbitals are involved in hybridization, this complex is called inner orbital complex or low spin complex. Like this, we can give the similar explanation even to the another complex called hexafluoroferrate 3 complex. Now in this complex, Fe is the central metal ion with primary valency +3 and secondary valency 6. Here the fluoroligand is a weak field ligand. Atomic number of Fe is 26 as usual. It is given in the previous complexes also. Its electronic configuration is 3d6 4s2. Fe in +3 state electronic configuration becomes 3d5, which contains all the 5 unpaired electrons in the 3d subshells. When the weak field ligand approaches nearer to the central metal ion, the unpaired electrons do not get paired up. As there is no vacant inner d orbitals, the outer 4d orbitals take part in hybridization. So therefore, in this case, we have sp3d2 hybridization because of the weak field ligand. It will not pair up the inner d orbitals. The vacant orbitals of Fe3 plus ion undergoes sp3d2 hybridization. Each fluoride ion ligand gives lone pairs of electron to the central metal ion. There are 5 unpaired electrons in the complex. Hence, the hexafluoroferrate 3 ion is having octahedral geometry with a bond angle of 90 degrees. And it is paramagnetic in nature. Since outer d orbitals are involved in hybridization, this complex is called outer orbital complex or high spin complex, because it is known as high spin complex because it contains unpaired electrons. Here we have 5 unpaired electrons. So this is about the explanation of valence bond theory with complexes having coordination number 6. Now coming to the other complexes of the coordination number 4. How to explain these compounds taking valence bond theory. Now let us take an example, tetramine zinc 2 complex. In this complex, zinc is the central metal ion with primary valency +2 and secondary valency 4. The ammonia is a strong field ligand. Atomic number of zinc is 30. Its electronic configuration becomes 3d10 4s2. Zinc is in +2 state, hence its electronic configuration becomes 3d10. and ground state electronic configuration, which gives 3d10, shows that all the d orbitals are completely filled. In zinc ion, d orbital is completely filled, hence there is no ligand effect on pairing of electrons. Since only 4 vacant orbitals are remained, therefore zinc 2 ion can accept only 4 lone pairs of electrons. Here zinc 2 ion undergoes sp3 hybridization. Each ammonia molecule gives lone pair of electrons to the central metal ion. There is no unpaired electrons in the complex, hence this complex is having tetrahedral geometry with a bond angle 109 degree 28 minutes and diamagnetic in nature. Coming to the another compound known as tetrachloronic 2 ion. In this complex, nickel is the central metal ion with primary valency +2 and secondary valency 4. The chloro ligand is a weak field ligand. Atomic number of nickel is 28. Its electronic configuration becomes 3d8 4s2. Nickel in +2 state, its electronic configuration becomes 3d8. The ground state electronic configuration of nickel shows that it contains the 2 unpaired electrons. When the weak ligand approaches nearer to the central metal ion, the unpaired electrons do not get paired up. Since only 4 vacant orbitals are remained, therefore nickel +2 ion can accept only 4 lone pairs of electrons. Here nickel 2 ion undergoes sp3 hybridization. Each chlorine atom gives lone pair of electrons to the central metal ion. There are 2 unpaired electrons in the complex, hence nickel tetrachloro complex is paramagnetic in nature. It is having tetrahedral geometry with a bond angle 109 degree 28 minutes. Let us take another example, that is the tetracyanonickelate 2 ion. In this complex, nickel is the central metal ion with primary valency +2 and secondary valency 4. The cyanide ligand is a strong field ligand and the atomic number of nickel is 28. Electronic configuration is 3d8 4s2. Nickel is in +2 state. Its electronic configuration becomes 3d8. Ground state electronic configuration shows that nickel 2 ion contains the 2 unpaired electrons. When the strong ligand, that is the cyanide, approaches nearer to the central metal ion, it gets excited so that unpaired electrons gets paired up. The excited electronic configuration of nickel gives all the 8 electrons gets paired up and it undergoes dsp2 hybridization. The vacant d orbitals of nickel 2 ion undergoes dsp2 hybridization. Each cyanide ligand gives lone pairs of electrons to the central metal ion. There is no unpaired electrons in the complex. Hence the complex is having square planar geometry with a bond angle 90 degree and it is diamagnetic in nature. Similarly, the same explanation can be given even to the cuprammonium sulfate complex also. This particular slide shows whatever I have explained earlier, the same thing. So various geometries with various hybridization. Below I have given the examples of the cobalt complexes, how this cobalt complex, the valence bond theory can be explained based on the electronic structures. So students, you must able to draw the diagrams like this. You have to practice these things. Here also in this slide also I have given the complexes which I have explained and how these explanation can be given in a another way, in a diagrammatic way. Here I have shown it. In this slide, it shows the tetrahedral complexes. So the tetrahedral complexes also have inner orbital and outer orbital complexes. Inner orbital complexes are those where the d orbital, 3d orbital is involved in the hybridization. That is, it gives dsp2 hybridization, and generally these complexes are square planar. And this inner orbital complex results when a ligand is a strong field ligand. For outer orbital complexes, generally the ligand is a weak field ligand and it gives sp3 hybridization, and the geometry will be tetrahedral. Now, the same explanation, try to give the similar explanation to the complex called the hexa-aqua nickel 2 ion. So, this is the homework for you to write the valence bond, apply the valence bond theory to this particular complex. Coming lastly, the limitations of valence bond theory. Valence bond theory cannot account for the relative stabilities for different shapes and different coordination numbers in metal complexes. Example, cobalt 2, it's a D7 system, forms both octahedral and tetrahedral complexes, while nickel 2, that is a D8 system, rarely forms tetrahedral complexes. Similarly, Fe3, that is a D5 system, forms both tetrahedral and octahedral complexes, while chromium 3, that is a D3 system, gives only octahedral complexes. The second limitation is valence bond theory cannot explain why copper 2 forms only distorted octahedral complexes even when all 6 ligands are identical. The third one, it cannot account for the relative rates of reactions of analogous metal complexes. The example is given. Valence bond theory fails to explain details of magnetic properties, including the magnitude of the orbital contribution to the magnetic moments. The example for this is the complexes with 3 unpaired electrons have magnetic moment value equal to 3.87 Bohr magneton. In tetrahedral complexes, this value is in the range of 4.4 to 4.8 Bohr magneton. And in octahedral complexes, it is in the range of 4.7 to 5.2 Bohr magneton. Valence bond theory fails to explain the increase of the magnetic moment value. Students, regarding this, I will explain the magnetic moment in the subsequent classes. The fifth one, valence bond theory cannot interpret the spectra of the complexes. Valence bond theory cannot explain the temperature dependent paramagnetics of the complexes also. In a brief way, we can also give the limitations of valence bond theory like this. It provides only qualitative explanation for complexes. It does not explain the variations of magnetic moment with temperature. It does not take into account the splitting of d energy levels. It does not predict the relative stabilities of different structures. It does not explain the color of the coordination compounds. It cannot explain magnetic behavior based on geometry. Does not explain why some called inner and outer orbital same metal ion in the same oxidation state. It fails to predict the exact geometry of the complexes with coordination number 4. The example I have given. So the cupramonium ion, it may exist in, why it exists in square planar, why not in tetrahedral case, the tetrahedral way. Dear students, so this is about, in my first lecture, I have explained the valence bond theory and application of the valence bond theory to the various complex ions, and lastly the limitations of valence bond theory. Thank you.